Hi guys, I think I'm audible. We can start the session, right? Yeah. Okay. So we can start the session. Hi guys. Let me share my screen. Okay. I think my screen is visible, right? Everyone. Can anyone confirm that? Okay, I think it's visible. So let me start the presentation. Okay. So let me once more check whether my video is capturing. Okay, yeah. Okay, so hi all. I'm Narayanan PP, research scholar from IIT Palakkad. So I'm assisting this course that is Unlock Circuits. So this is the week second courses or the syllabus being taken, and the course instructor is Professor Jayanta Mukherjee. So I once again welcome you all. So in the previous the week second session or the syllabus, sir has covered mainly I guess the non-idealities regarding the op-amps, then the Bode plots, the concepts of Bode plots and frequency response. So we'll be solving few questions which is related to only that week portions, that is week 2 portions, and also it will help you in solving the week 2 assignments, also to understand a few concepts, as sir has taken all the concepts during the week 2. So we'll start with that. So let me start with the questions. So I have collected 10 questions for solving, and we'll start with the first question here. So first question is to determine the gain of the circuit shown below. Determine the gain of the circuit shown below, and it is given that the R1, the resistance R1 is 1 kilo ohm, RF is 10 kilo ohm, and the gain is 100 dB. So this is the circuit. From here, so we were dealing with the non-idealities, right? So from here itself we can say like it is non-ideal. See, the gain is 100 dB, right? So usually for an ideal op amp the gain will be infinity, right? So here the gain is 100 dB, which means it's a non-ideal op amp. Okay, so we'll see how the gain of such an amplifier, non-ideal amplifier is calculated. So you would have gone through the video, so the same step we will follow here. So since it's a non-ideal op amp and it has a gain 100 dB, 100 dB means like say if the gain of the amplifier is say A, so this is the gain A, then 20 log of A is equal to 100 dB. So that's what is given here. So 100 by 20 is 5, so A will be equal to, since log is, the base of log is 10, so A will be equal to 10 power 5. So the gain of this amplifier is actually 10 power 5. Okay, so that's what we have understood from this gain. So we'll see what is the net gain, total gain of the circuit, or the circuit gain. So that is, this is the circuit, entire circuit, and this is the output V0. So what is the gain? G equal to V0 by V1. So this is what we have to determine. Okay, so we erase it. So what we have got here is A equal to 10 power 5. So as sir has mentioned, in the same way, in the same step we will follow, that is, say if V1 is the input voltage, then say due to its non-ideality, though the non-inverting terminal is grounded, there will be some voltage difference, though it may not be V1, so there will be some voltage set to V2. Okay, so actually if it is an ideal op amp, whatever is the voltage here, that should be followed here, right? But we will say like there is a voltage difference, say V2, with respect to this ground. So So what happens, like since the gain of this op amp is A, and the voltage between this terminal, like the inverting terminal is having voltage V2, and the non-inverting terminal is having voltage 0, right? So the ground. So what will the output VO in terms of V2? VO will be equal to the gain A into whatever is the non-inverting terminal voltage, that is 0, minus the voltage at the inverting terminal, that is V2. So it will be equal to minus A into V2. Or from here we can say like V2 is equal to minus VO by A. So that is what we have understood, what is the voltage V2 in terms of VO. Okay. Okay, so that's what we have got. Now we'll see, since V2 is the voltage, so what we require is like V0 by V1, right? V0 by V1 is the requirement. So we'll see what is the relation between V1 and V2 here. So since V1, the voltage at this point is V1 and voltage at this point is V2, the current I through this resistance R1, we can say like I equal to, say I equal to V1 minus V2 by R1. So we have got from here like V2 is equal to minus V0 by A. So V1 minus V0 by A by R1, or it will be equal to V1 plus V0 by A by R1. So this is the current I flowing, and the same current, since the current here into this terminal is 0, or they have not mentioned, or the question has not mentioned that its bias current is it's having some bias current, so we'll assume that it is 0. So what is the current through the feedback? The current through the feedback will be I. Okay, so from here we can determine what is the voltage V0, right? So what is the voltage V0 from here, that we will see. So what is the voltage V0? V0 is since the current is flowing in this direction, the voltage drop across RF will be plus minus like this. The polarity will be plus here and minus here. So what is the voltage V0? V0 is the voltage across this RF. So that is voltage across RF is with respect to this point is minus I into RF, I into RF, and also at this point the voltage is V2, right? So plus V2, so that is the voltage V0. So I into RF plus V2. So again we will substitute what all current we have, the current as well as the value of V2 from the previous value. So what is I? I is like minus, I is V1 plus V0 by A whole by R1, and V2 is minus V0 by A. Okay, so that's what we have got. So by rearranging this, we will get what is V0 by V1. See the terms, there are only terms relating V0. So this is V0 and V1. So we can just rearrange these terms and we'll get like if I let me expand this. So V0 equal to minus, so there is RF also which I have left. So minus V1 RF by R1, okay, plus so minus V0 by A into RF by R1, okay, and minus V0 by A. So we can rearrange these terms and we'll get what is the relation between V0 and V1. So that's how we will get the gain. So I have solved this term, so we'll get V0. So this was the term where we reached earlier. So this is the term where we reached earlier, and by rearranging we'll get V0 by V1 equal to minus RF by R1 by 1 plus RF by R1 into 1 by A. So this is the gain, net gain of this amplifier. So let me erase all these terms what I have written. So by solving in the method that we have followed, we got the gain G as this term. So V0 by V1 as minus Rf by R1 by 1 plus Rf by R1 by 1 by A. So since A is not, if A is equal to infinity, this term will be 0, and it will be minus Rf by R1. So that is what we have done earlier in the week 1 when we assume the op amp as ideal. So for inverting amplifier, the gain should have been minus Rf by R1. But here, since the gain is not infinity, the gain will be in this format, minus Rf by R1 by 1 plus Rf by R1 into 1 by A. Okay, so since all Rf terms, R1 means Rf value, R1 value, and the gain A is also we have found what is the gain A from this term. We will substitute that terms here and we'll get the gain G as equal to minus 9.99. So it is almost equal to minus 10, right? So Rf is minus 10 and minus 10k, and R1 is 1k. So it is almost equal to minus 10, but still it is not correct 10. So there is a small change. So if the gain is again, if gain is 10 power 6 or 10 power 8, it will near the value of the ideal gain of a inverting amplifier. So when A is lesser than that, this gain will be more or less, like it will be near to 9.8 or 9.7. So that's how we'll find the gain of a non-ideal op amp. So in order to have, like if we are designing a circuit or designing a circuit where the gain must be approximately equal to the ideal gain, we have to select the amplifier or op amps which is having this gain, that is open loop gain, to be near to very high, like 100 or 1000 dB if possible. So we'll get approximately the ideal gain that we have designed. So this is how we will determine the gain of an amplifier when the amplifier is non-ideal. That is given the gain is some value, some so and so dB. Okay, so now let's go to the second question. The second question is same one. See, like determine the input resistance. Like the question is regarding the same circuit. Well, the question is just to find the input resistance of the circuit. Okay, determine the input resistance of the circuit shown below, and given the resistance value R1, Rf and gain values are same. R1 equal to 1k, Rf equal to 10k, and gain equal to 100 dB. So here the question is to find the input resistance. So what is the input resistance? Input resistance is the, say for example, this is a circuit. Okay, this is a circuit, and we have given an input voltage V1, and due to that this circuit will means the current will flow to the circuit through this source, right? So say for example the current I1 is the current flowing to the circuit through this voltage source. So that is a voltage taken from this source. Okay, so if it is so, what we'll do, what is the input resistance of this circuit? Input resistance Zin or impedance Zin is equal to the input voltage V1 by input current I1. So this is the input resistance. So that's what we are going to find. So that's what we are going to find. Say since there are no other capacitor or inductive components, we will say it as input resistance Rin. Okay, so instead of Zin, so Rin will be equal to V1 by, so say the current through R1 is I1. So V1 by I1 is the input resistance. Okay, so since the circuit is non-ideal, and we have assumed like the voltage here is V2. So what is I1? I1 is equal to the voltage across this resistance, that is V1 minus V2, right? So V1 minus V2 by the resistance R1. Okay, and from the previous circuit we have found, like since the gain of this amplifier is A, so V2 will be equal to minus V0 by A, right? So we will substitute that here. So V1 minus, so V2 is minus V0 by, so minus V0 by A by R1. Okay, so that equal to V1 plus V0 by A whole by R1. Okay, so since we have derived the gain of this circuit, so gain equal to V0 by V1 was equal to how much? Minus Rf by R1 by 1 plus, it's like Rf by R1 plus 1 into 1 by A. I guess it is the same, right? So yeah, Rf by R1. Okay, so that was the gain that we have found out. So we'll substitute this since it is the gain. So what is V0? V0 equal to V1 into gain, right? So we'll just substitute this value here. So we'll substitute this value here. Okay, so what we'll get is like I in, like I1 equal to, so I will just change the color. Okay, I1 equal to V1 plus, so V1 into G, right? So V1, say we'll take V out as V1 into this gain. So let it be G itself for easiness. Okay, so I will drop this. Okay, so V1 into G by A by R1. Okay, so so this will be as given as I1 equal to V1 into 1 plus G by A by R1, right? So what is the input resistance is V1 by 1. So what is V1 by 1 from this relation? V1 by 1 will be equal to R1 by just rearranging, right? So 1 plus G by A. Okay, so this will be the input resistance Rn equal to this one. So substituting the gain value, so here the gain value, if we substitute that, what we will get? R1 by 1. So gain is minus hello, it's not visible. Okay, is it not visible to anyone? Okay, let me check. Okay, it's shown like no one is able to see. Can anyone else please message? It's visible. Okay. I think you may please check your net connection also. Okay, thank you. Okay, so I will continue with that. So I think from my end it is shared. I think please check your internet connection also. Maybe some issue with my internet connection. Let me check. It's fine only. Okay, the thing is like I am recording this video. I will upload it in my channel, and I will just means I think NPTEL has shared that link, right? So if any part is not visible, please go through that also. So we'll continue with this. So if no one is able to see, means I will just reconnect the entire session. Okay. So we were substituting this value G here. So G is like minus Rf by R1. So plus minus Rf by R1 by 1 plus Rf by R1. Sorry for my handwriting. Plus 1 into 1 by A, and there is A factor here. So I will just substitute that also. So this into 1 by A. Okay, so this is the input resistance. So this is how we will find the input resistance. So I have done I have solved here. So I just clear this whatever I have written here. So let me clear that. Okay. Okay, I think. Okay. Okay. Yeah. So this is what means I have cleared what I have written. So this is what I have done. So I will again mention like we have found earlier. Sorry. Yeah. So we have found earlier what is the V0 by V1 gain, and what we did is like we found the current I, and current I is, like, say if this is a voltage V2, V1 minus V2 by R1, that is a current, and we substituted V2 as minus V0 by A, and this V0 I substituted from here, that is from here V0 is V1 into G, right? So I just substituted and rearranged, so I will get some input resistance Rn as this term. So it is pretty much straightforward, we can do that. I think it's clear for you. So on substituting, since the values are given, R1, RF and the gain value is given, on substituting we will get Rn is equal to 1000 means 1000.09 ohm, so as written here. So but like if it was ideal, say the gain is equal to infinity, what is the gain, what is the input resistance, we used to how we used to find, the thing is like we assume or since the gain is infinity, we assume that this is 0 volts, so this is also grounded, right? So what is the input resistance? The input current is like V1 minus 0 by R1, that is current I1. So V1 by I1 will be equal to R1. R1 is here 1K. That is when it is ideal, that is 1000 ohm, right? But since this is non-ideal, we will get as 1000.09 ohm. So that is a small change, but still that is the input resistance of this circuit. So if the gain is less, like this is 100 dB, that's a reason, that is A equal to 10 power 5, it is huge. Like if it is 10 power 3, the resistance will be more, so there will be difference in the resistance. So that's how we will find the input resistance. Okay, I think it's clear. We'll go to the third question. Okay, I think first and second question is related and it's pretty much straightforward. Now coming to third question, the an op-amp has a gain bandwidth product of 10 megahertz. Okay, find the bandwidth of the inverting op-amp which has a gain of 80 dB. So we know, like say this is the frequency response of an op-amp, then and this is the bandwidth. This is the bandwidth and this is the gain of the op-amp during its pass band. The gain is A. Then what is the gain bandwidth product? Is A into bandwidth. That is the gain bandwidth product. So given A into BW is given as 10 megahertz. Okay, and also A is given in dB. So it is like 20 log A is given as 80. Okay, so how we will find? So it's like 4 times 20 into 4 is 80 and log is to the base 10. So what is A? A will be equal to 10 power 4, right? So A is 10 power 4. So and also given the gain bandwidth product is 10 mega. So A we got as 10 power 4 into bandwidth equal to 10 mega. So 10 mega is 10 into 10 power 6, right? So what will be the bandwidth? Bandwidth will be equal to 10 into 10 power 6 by 10 power 4. Okay, so this is 2, so it will be 1000, or the bandwidth is 1 kilohertz. So given an inverting configuration gain we have made is 10 power 4. The gain A is 10 power 4, which means its bandwidth is reduced to 1 kilohertz. That's the thing. So that is what we understand from this this question. So that is what I have solved here. The gain bandwidth product is 10 megahertz. Again, as mentioned here, the A value will be 10 power 4. On substituting that, we will get bandwidth as 10 power 3. That is 1 kilohertz. Okay, so it's a simple question. The third question. So coming to the fourth question, I think it's clear to you all. Fourth question is find the output voltage V0 for the circuit shown below. So there is a circuit shown here. It's an op-amp based circuit, and it's said like the offset voltage VOS of offset voltage VOS equal to 10 millihenry. The input voltage Vin is 1 volt, RF is 22 kilo ohm, and R1 is 2.2 kilo ohm. So this is a circuit, and it is said that it is having an offset voltage. So it's a non-ideal op-amp, and it is connected to here. So as shown in this circuit, it's connected to this non-inverting terminal. See, and this V naught is 10 millivolt. So the question is to find the output voltage V naught. So how we will find output voltage? Say suppose there is some current flowing like this, IF. Okay, so the drop across this resistance will be plus minus, right? So what is the output voltage? Output voltage will be the voltage drop across this resistance, right? So we'll see voltage drop across this RF and the voltage at this node. At this node it is actually what? At this node it is VOS. So VOS. So what is the voltage V naught? V naught will be equal to the voltage across RF. So this is the point output. So it is negative polarity. So minus IF into RF plus what is the voltage at this point, that is VOS. So this is actually the output voltage. So we need to find each of these values. It is being given, like RF is given, VOS is given, we just need to find what is IF. So what is IF? Since the current is flowing like this, so I will just change the color. Okay, so the current is flowing from IN, right? So current is flowing in this direction, and since there is no means it is not mentioned like there is any bias current here, so we assume that the bias current here is 0 ampere. So the entire current, say this current is I1, so the entire current I1 will flow through this to this path, so which means IF is equal to I1. Okay, so what is I1 here? I1 is the current flowing through this resistor, right? So what is the current through this resistor? The voltage across that resistor by that resistance. So what is the voltage drop across this resistance? So this point voltage V. So V in minus the voltage at this point. At this point the voltage is VOS. So V in minus VOS by the resistance R1. Okay, so this is the current through the through resistance R1, and that is equal to IF, right? So substituting this, we'll get V naught equal to IF minus IF, right? So minus IF is V in minus VOS by R1. So this is the current IF, that into RF, and plus VOS. So on substituting, like given V in as 1 volt, so minus, so 1 volt, VOS is 10 milli, that by resistance R1 is 2.2 K and RF is 22 K and VOS is 10 milli. Okay, just need to substitute that and we'll get some value. Okay, so that is the value. If we substitute correctly, we'll get the output voltage V naught as minus 9.89. So that's how we solve this question. So I will once again brief how we did. The requirement is to find V naught, and how we will find V naught? We will find what is the voltage across RF. So since the current is flowing in this direction, the voltage drop across this will be like this, plus minus. So if the voltage here is VRF, and what is the voltage at this point? This point the voltage is VOS. So what is V naught? V naught equal to VRF, not VRF, minus VRF. Polarity is just opposite. Minus VRF plus VOS. And what is VRF? It is IF into RF. Okay, so we'll find what is IF from this by noting what is the current through the resistance R1, and we'll substitute and we'll get the value of V naught as minus 9.89. So this is how we'll find the output voltage of a circuit whose offset voltage is given. So suppose like though it's not given, for fun we'll just see how the output voltage V naught we can find if they have mentioned the bias current. Say for example they have given like IB minus as say some 10 nanoampere. Okay, and IB plus as, again let it be both be equal, so IB plus equal to 10 nanoampere. So in this case, like it is not the same as the same question, but say for example they have also mentioned like the IB. Okay, IB plus equal to IB minus equal to 10 nanoampere. So what we will do? The only thing is like we have to subtract this current. So the same way we have to find, we will find what is the voltage across RF and will add with VOS. So but here we have been given the bias current. So this is current is IF, right? So what is IF? So say this current I1. Okay, so what is IF here? IF equal to I1, and from here some current is flowing inside, right? So that is minus IB minus. So we have to substitute this value. So again I1 we can find in the same way. I1 equal to V in minus what is the voltage, that is VOS, right at the inverting terminal, VOS by resistance R1, that is the current I1, and IB is 10 nano. So you just need to substitute this 10 nano in that equation and you will get appropriate voltage V out. So that's how we will find the voltage V naught when even the bias current is given. So that's about the question 4. I think it's clear to you all. We'll go to the next question, that is question number 5. Determine the value of resistance R2 such that the effect of bias current is nullified. So given that given to find that what is the resistance value of this R2 if the bias current is given, like whether bias current is given and we need to nullify that effect of bias current. So where to nullify the bias current, means effect of bias current? The thing is, like, see, there is no voltage source connected here, right? The current source here is like ground, so 0, input is 0, so output must be actually 0. But the thing is, like, since there is a current IB1, IB minus through this part and IB plus through this path, there is a current flowing like this. So it will definitely, it will create a voltage IB minus into RF. So that current will be in there. Okay, so this current, not this plus, it will be an effect of IB plus also. So the output won't be equal to 0 when if R2 is not correctly chosen. So the question is to determine R2 such a way that the output voltage V0 is equal to 0. That is what it is meant, like to nullify the effect of bias current. So given the bias current IB minus as 10 nanoampere, IB plus as 10 nanoampere, okay, some constant, okay, and RF equal to 10K and R1 equal to 1K. So we need to find what is the value of R2. Okay, so how to find that, we'll see. So before that, we'll assume, or since it is given that the current through this path is IB minus, so we'll draw one source here. So there is one current, source, this is IB minus, and there is one current source like this, this is IB plus. Okay, so since there is a current IB plus flowing through this path, definitely there will be a voltage drop like this, plus minus, and what is the voltage drop? R2 into, it is IB plus. Because of this voltage will have a not voltage, due to this current there will be voltage at this point, and that point is, what is that voltage? IB plus into R2, that is minus of this, that is minus of voltage across R2. So this is the voltage at this point, and the same point, the same voltage will be followed here. So what is the voltage here now? That is IB2 R2, means minus IB2 R2. So since such a voltage is there at this node, there will be current, similar current flowing in this direction through R1. Okay, so you can say what is the current, this current will be equal to the voltage across R1 by resistance R1. So minus IB2 by R2, that is the voltage by R1. Okay, so that is the current through this R1. Okay, so that is the current, and since this is since the current direction is assumed like this, so it must be the voltage must be assumed like this, right? So it will be minus of minus, so it will be IB2 into R2 by R1. So that is the current, this current. So this will be that current. Okay, so we got the current through R1, and what we need to find is voltage V0. So what is V0? V0 is a voltage across the resistor RF. So for example, there is a current IF flowing through the RF. There will be voltage drop like this with polarity this. So V0 will be equal to IF into RF. So minus IF into RF plus what is the voltage drop across this point. So minus IB plus into R2. So we just need to substitute these values. So these are IF. Okay, so we just need to substitute this value. So but we need to find IF also, right? So what is IF here? IF is equal to, so since there is a current flowing like this, so I'll just change the current. So there is a current flowing in this direction, and from that some part is taken into the op amp, that is IB minus. So what is IF? IF will be equal to, so the current, this current, so this is actually plus IB2 R2 by R1. Okay, and what is this current? That is minus IB1, IB minus. So this is current IF, and on substituting this here, V0 equal to, we'll get IB2 R2 by R1 into RF minus IB minus into RF. So I just substituted in the first term, okay, and minus IB plus R2. Okay, so the question is to find the value of R2, such that V0 is equal to 0. So just substitute V0 equal to 0. Okay, and we know IB minus and IB plus are equal. Since IB minus equal to IB plus equal to 10 nano, we can substitute that and substitute V0 equal to 0 and just rearrange. We will get the value of R2 as equal to R1 into RF by R1 plus RF. So you will get like this. You just need to rearrange these terms. Okay, rearrange these terms. We will get R2 equal to R1 into RF by R1 plus RF. So this is how we will find the effect, means value of R2 such that the effect of the bias current is nullified. Okay, I will just clear these terms and I will show the solution that I have written. So as I mentioned initially, I found what is the current IR1. So that what is the current IR1 we have to find. So for that we need to find what is the voltage here. So voltage here is R2 into IB plus, okay, minus R2 into IB plus, and that is the same voltage here. So that by R1, so minus of that by R1. So I will get R2 IB plus by R1. So what is current IF? The current IF is this current minus IB minus. So whatever current flowing through IR1, say IR1 minus the current IB minus. So that is what written here. And what is voltage V0? V0 is the voltage across the resistance RF, that is minus IF into RF, and the voltage at this point, that voltage at this point is minus R2 into IB plus. So we will just substitute this here and we will get this term. That is, this is where we stopped, and I just rearranged it here and I substituted V0 as equal to 0. And when V0 is substituted equal to 0, this term will be equal to 0, right? This term will be equal to 0. So this term equal to 0 means if I just rearrange it, we will get R2 as R1 into RF by R1 plus R2. So this is the net resistance of R2 that should be substituted there such a way that the effect of bias current is nullified. And on substituting that, we will get the net resistance R2 as 0.909 K. So 909 ohm. So it's near to 1 kilo ohm. So this is the this is how we will find the resistance, or this how we nullify the effect of the bias current here. So in these circuits. Okay, so this is about the question 5. Now let us go to the question number 6. So this is this question is related to body plot. We will check that. So the question is, the given the transfer function of a system to be T of s equal to 15 to 0.01 s plus 1 by 0.1 s plus 1 into 10 s plus 1. Determine the corner frequency of the function. Okay, so before coming to this question, like this transfer function, let us write the transfer function in general. So transfer function of a system in general we can write like T of s equal to some constant a into s by z1 plus 1 into S by some Z2 plus 1 etc. into S by say some Zn plus 1 whole by S by P1 plus 1 into S by P2 plus 1 etc. into S by Pn plus 1. So where Z1, Z2 etc. Zn are the zeros, are known as the zeros, and P1, P2, etc. Pn are known as the poles of the system, So here, and A is the some constant when for example when S equal to 0, what will be the transfer function? T of 0 will be equal to A into 1 into 1 into 1, so A into 1 by 1 into 1 into 1, so 1. So T of 0 is equal to A. So A is equal to, means A is the value, a constant when S equal to 0. What is S equal to 0? S is actually j omega, right? So that is the value of omega is 0, that is frequency. When frequency is 0, omega is 0. So when the frequency of that system or the input of the system is 0, the value of T of S at that value is A, that is the constant. So that is actually the gain of the system when S equal to 0 or the omega is equal to 0. So that is the value. And what is Z1, Z2, Zn and P1, P2, Pn? They are zeros and poles, and those are the values, or those are the frequency values at which there is any roll off happening. So for example, if there is a system and I have a frequency response like this, so these are the change in the roll off, right? So this say for example this is minus 60 dB per decade, and this is say minus 40 dB per decade. So there is a change in this roll off per decade, value change is there. So at what point it happens, at what frequency it happens, that is known as the corner frequency. So this is the corner frequency. So we have to find the value of this corner frequency. For example, this Z1, Z2, Zn, P1, P2, etc. Pm are known as the corner, though it is zeros and poles, they are the corner frequency at which the system behaves in a particular manner. For example, if the corner frequency is at happening at Z1, what happens is there will be the roll off will be plus 20 dB, right? Plus 20 dB. I think you would have gone through the lecture. So when the corner frequency is zeros, Z1, Z2, etc. Zn, then the roll off will be plus 20 dB per decade, and when the frequency is at P1, P2, etc. Pm, the roll off will be minus 20 dB per decade. So that is what we have seen earlier. So here what the question is to find the corner frequency of the function. So from here itself we can find, right, from the question itself we can find what is the roll off. That is just the we just need to see these terms. Okay, so I will take another color. Okay, so from this transfer function I can write it as, we can rearrange in the similar manner. Okay, in the general similar to our general function as 50 into S by, right, what is 0.01 S by, it is 100, right, S by 100 plus 1, and how I'll write this 0.1 S, so it is S by 10 plus 1, and this is 10S, and 10S means S by 0.1, okay, 0.1 plus 1. So from here itself we can say what is the 0, right? So what is 0 here? This Z1 equal to 100. What is here? Here it is P1 equal to 10, and say this is P2. Say P2 equal to 0.1. So these are the frequency. So 0.1 is one frequency, 10 is one frequency, and Z1 is another frequency. So these are the three frequency at which means three corner frequency of that particular system. Okay, so this is how we will find the corner frequency of that particular system, and that is what I have written here in the solution. Okay, I'll just rub it all. Okay, so that is what I have written here. Initially this is T of S, and what is omega 1? Omega 1 is T1 by 10. So I have written in ascending order. So where is 0.1? That will be not 0.1, I'm sorry. Okay. Okay, so which is the least one, so that is least frequency, that is because of coefficient of this one, that is 10. So 1 by 10 is 0.1, 1 by 0.1 is 10, and 1 by 0.01 is 100. So I have written ascending order. So these are the corner frequency of that system. So this is the answer or the solution to this question. So it's a straightforward question. So we'll go to the next question. The question is, find the transfer function in terms of S, that is we need to find T of S if the body plot for the same is shown below. So the body plot is shown here. We need to find what is the transfer function. So as explained earlier, T of S equal to some gain A into S by Z1 plus 1 into S by Z2 plus 1 plus etc. Not plus, into, right, into etc. S by Zn plus 1, that by S by P1 plus 1 into S by P2 plus 1 etc. S by Pm plus 1. So as I mentioned earlier, the value of A is when S equal to 0. So for example here S equal to 0 means at which omega equal to 0, the value of when the omega is equal to 0. So here from the body plot at 0 the value is 20 dB. Okay, so this is 20 dB. So given here is actually 20 log. So 20 log of A given here is 20 log of A is here given is 20 dB. So what is A? So 20, 20, so it is 1. So since the base is 10, A will be equal to 10. So A is 10. Okay, now we need to find Z1, Z2, Zn, etc. Zn, and P1, P2, etc. Pm. So to see that, we'll just see how many number of poles are there and how many number of zeros are there from this plot. So we know, like before that we should know how the zeros changes the body plot and how the poles change the its roll off in the body plot. So we know the zeros, if there is a 0 Z1 then or a corner frequency due to 0, then the roll off will be like plus 20 dB, right? It will be like plus 20 dB. And if there is some poles P1, P2, etc., that will create minus 20 dB roll off. Okay, so as we can see in this graph, so initially at omega equal to 0 it was 20 dB, and at frequency 10 the roll off started to be minus 20 dB per decade. So at this point what will be? It will be a pole P1. So that P1 is equal to 10. So there is one pole at 10, and now coming at 60. At 60 what happens is the roll off became 0 dB per decade. So how 0? So it is like minus 20 plus 20 is 0, right? So at this point at 60 there is some plus 20 dB decade, right? 20 dB per decade roll off is there. So how that came? That must be only because if there is a 0, say, so at 60 is the Z1. Now at frequency 100 again it started going down, right? So at this point again there is some pole P2, and what is the roll off? That is minus 20 dB per decade. That is the roll off. So that will be again first order component. So how many number of poles and zeros are there? There is 1 0 here. So let me take under color. So 1 0 is there Z1, and 2 poles P1 and P2 is there. So in general we can write T of S equal to, for this transfer function, as A into S by Z1 plus 1. There are no other zeros, right? So by S by P1 plus 1, and there is one more pole, so S by P2 plus 1. So this will be the transfer function. And what is the value of A? A is 10 into S by Z1. Z1 is what is Z1? 60. So S by 60 plus 1 by what is P1? S by 10 plus 1. Okay, yeah. S, and what is P2? S by 100 plus 1. Okay, so this will be the transfer function of this body plot. So let me clear this. I will show the solution that I have written. So same that I have mentioned, like this will be the poles P1, this will be 0, 60, and 100 will be the pole P2, and I just substituted here. So since there is only one pole and two, 1, 0 and 2 poles, we can write the transfer function as like this, and I just substituted each values, and I got the transfer function as 10 into s by 60 plus 1 by s by 10 plus 1 into s by 100 plus 1. So this is the transfer function of this body plot. So it's pretty much simple. I think you can do it again. I think it's clear. We'll go to the next question. The next question is plot the body and magnitude plot for the following transfer function. So here they have mentioned to draw the body plot. Okay, given transfer function is this, we need to draw the body plot. So while drawing the body plot, we always, since it's a magnitude plot, right, so we always write in dB terms. So 20 log of t of s, 20 log of t of s, that is in dB. So this is what this versus omega, this is the body magnitude plot, and given we'll find what all are these zeros and poles here. So as we can see here, this term will only create the 0, right? So s by 1. So what is z1? Z1 equal to 1. So this is one corner frequency, and here is like P1. So P1 equal to, it is 1 by 0.1, right? 1 by 0.1. So it is 10, and from here, what is, again there is one more pole, that is P2 equal to 1 by 0.2. So this will be 5. So there are three corner frequency. One is Z1 at 1, and one at P2 5, and another at P1 10. Okay, and what is the initial value? That is when initial value is when s equal to 0, when or omega equal to 0. When omega equal to 0, t of 0, the value is 1000, right? When s equal to 0, in each case t of 0 will be equal to 1000. So what is 20 log of this term? 20 log of 1000, or 10 power 3, right, base 10. So what will the value? Value will be 60 dB. So definitely if there is no frequency, or when the frequency is 0, it will start at how much dB? 60 dB, right? It is 60, sorry, 60 dB. So definitely it will start at 60 dB. Okay, and the initial roll of frequency, or the corner frequency is 1, right? So there is one at 1, one corner frequency at 1, another corner frequency at 5, and another corner frequency at 10. Okay, so at 1 till 1 it is actually 60 dB, right? So from 1 there is a change, and what is the change? The change is like the 1 is due to a 0, right? So the change is positive, so plus 20 dB till what value? Till the frequency 5. So there will be 20 dB change here, plus 20 dB per decade roll off will be there till the frequency 5, because at 5 under corner frequency is there, or under pole is there. So at under pole P2, or the corner frequency P2 5, it is pole, so it will create minus 20 dB roll off. So since it is 20, so plus 20 was the earlier one, from that it will create a minus 20 dB. So plus 20 minus 20, it will create 0 dB per decade. So at 5 it will create a 0 dB, that is there is no slope, and at till what frequency it will be there? Till the frequency 10. So till 10 the slope will be 0. Okay, now at 10 is like due to the pole P1, that is this term 0.1 s plus 1 whole square. So there is a term square also. Okay, so due to this term there will be again a roll off. So what will the role of here, since there it is square term, so it is like 0.1 s plus 1 whole square, right? So this can be given as 0.1 s plus 1, that into again 0.1 s plus 1. Okay, so each of this pole will create minus 20 dB, right? This minus 20 dB plus this term will again create a minus 20 dB, so minus 20 dB. So what is the net effect? Net effect will be minus 40 dB per decade. So minus 40 dB per decade. It's not dB, it's actually dB per decade. So it will create from frequency 10, the roll off will be, net roll off will be minus 40. So minus 40 dB per decade. So this will be the so there is no other term. So this will be the Bode magnitude plot of this transfer function. Okay, so that's what I have drawn here. I will just clear whatever I have drawn now. Okay, so this is the one. So there is 3 cutoff frequency, 1, 5 and 10. Till 1 it is like when s equal to 0 it is 60 dB, and from 1 it is 0, so the roll off will be plus 20 dB, and at 5 it is a pole, so it will create a minus 20, so 20 minus 20 is 0, so 0 dB per decade, and at 10 is a pole, so it will create a negative roll off, and since there are two terms s 0.1 s plus 1 whole square, so it will create minus 40 dB per decade. So this will be the Bode magnitude plot. So that's all about the question number 8. Now let us see what is the question number 9. The question number 9 is determine the value of n. So determine the value of n for the transfer function t of s whose phase plot is shown below. So given the transfer function t of s equal to 100 by s power n into s plus 10, and its phase plot is given. Okay, phase plot is given, and it is asked like what will the value of n such that we will get such a phase plot. So that is what, so we need to determine what is the value of n. So how to find the phase of, or the phase of this transfer function? So we can write t of s as t of j omega s equal to 100 by, it is j omega power n into j omega plus 10. So this is t of j omega. So what is angle t of j omega? Angle of t of j omega will be equal to, so numerator there is no s term, so the angle due to numerator term will be 0, right? 0. Now regarding the minus the denominator angle. So what is first term angle? So there are n terms of j omega. So what is angle of j omega? J omega is like tan inverse, real term is 0, right? 0 by j omega or 0 by omega. So it will create how much? The angle will be 90. So there are n terms, there are n number of j omega terms, so it will create how much? So it will create n into 90 angle, so n into 90 degree. Okay, so minus of n into 90. Okay, so I have given a bracket here. Okay, plus what is the angle due to this term, that is this term. So tan inverse real term is 10, okay, by imaginary term is omega, so 10 by omega. So this is the angle, so we can write as minus n into 90 degree, okay, plus tan inverse of 10 by omega. So this is the angle. So this is the angle of t of j omega. Okay, now we need to find the value of n, right? So how to find the value of n here? So as we can see here, okay, so okay, when omega is equal to 0, okay, okay, I think I have made a mistake. I am sorry, I have made a mistake here. It is not tan inverse of real by imaginary, it is tan inverse of imaginary term by real term, right? I am really sorry. So it is 10 omega by 0. Okay, so what is the angle of j omega? It is actually tan inverse of omega by 0, so it is equal to 90 degree, real term by imaginary term. And similarly here also I have done a mistake. So what is the angle due to here? It is tan inverse of omega by 10. So I will just clear and write once more. I am really sorry for that. I will write again. So angle of T of j omega equal to 0 minus, okay, so n into 90. Why 90? Because the angle of j omega is equal to tan inverse of imaginary term is omega, right? By, not j is not there, omega by real term is 0, so it is 90. So there are n number of this term, that is s term, that is j omega power n, so n into 90. Okay, plus what is the angle of this term? So this is j omega plus 10. Okay, so if I substitute it, it will be tan inverse of omega by 10. So I am really sorry, I made a mistake there. So this is correct value. Okay, so how to find the value of n here? Okay, so how to find the value of n here? So from the response here, since this is 0, right? This is 0. So at omega equal to 0, the angle of Tj omega is equal to 90 degree, right? Not 90, minus 90. So substituting this, we can write as at omega equal to 0, this will be minus 90 degree. LHS will be minus 90 degree. That equal to here minus n into 90 plus tan inverse omega. So tan inverse omega is 0. So tan inverse 0 is 0, right? So 0. So minus 90 equal to minus n into 90. So what is the value of n? So n will be equal to 1. So what is the value of n here? So n value is equal to 1. So this is how we solve this question. So in order to solve this question, we just initially find what is the angle of this transfer function, and we'll substitute the frequency omega to 0, since we know what is the value of omega at 0, and we'll get the value of n. So this is how we'll find the value of n. I think it's clear to you all. I have written the solution here also. So this is the transfer function. The phase will be equal to minus n into 90 minus tan inverse omega by 100, and we'll substitute for omega equal to 0, and we'll get phase as minus 90 degree. And substituting this, we will get minus 90 only when n equal to 1. So this is how we will solve this question. Okay, now coming to the question number 10. So this is all about 9th question. Now coming to question 10. The question 10 is calculate the value of R1 and R2 of the bandpass. Calculate the value of R1 and R2 of the bandpass filter shown below. So this is the bandpass filter, which has FH minus FL. FH minus FL is the frequency, higher frequency minus lower frequency. So it's actually the bandwidth. Okay, so bandwidth equal to 20 megahertz, and the lower cutoff frequency is 10 megahertz, which is FL, right? FL is the lower cutoff frequency. So this is so what we need to find is calculate the value of R1 and R2. So this is the circuit. In the circuit, the capacitance value is given 3 picofarad, 3 picofarad. Okay, resistance R1 and R2 is not given, so we need to calculate the R1 and R2, and given that its bandwidth is 20 megahertz and its lower cutoff frequency is 10 megahertz. So we can find that. So from the given data, we'll deduce something like we know, since this is a band pass filter, its body plot will be somewhat like this, right? So this will be the lower cutoff frequency FL, and this will be higher cutoff frequency FH. FL equal to 10 mega, and given FH minus FL is 20, right? So what is FH? FH will be equal to 30 megahertz. So that we have got from here, 30, and FL is 10 megahertz. Okay, now how to find the R1 and R2? So sorry. So from here we'll find what is the transfer function. That will be easy, right? So what is the transfer function here? T of S equal to V naught of S by v1 of s. Why we are going to find transfer function? Because if we know transfer function, we will get which all terms create the lower and higher cutoff frequency, right? So that's why we are going to find the transfer function t of s equal to v0 of s by v1 of s. So this is, since this is a like inverting amplifier, so this is one impedance, say z1, and this is the another impedance z2 in feedback. So what is v0 of s by v1 of s? v0 of s by v1 of s is like z2 of s by z1 of s minus of z2 of s by z1 of s, since it's an inverting configuration. So from here we'll find what is z1 of s and z2 of s. Okay, so what is z2 of s? We'll find what is z2 of s. Since z2 of s is like the parallel combination of this capacitor and resistor, right? So say the capacitor, since both capacitors 3 picofarad will denote as C, both as C. So we have in Laplace domain it is like 1 by SC. Here also Laplace domain 1 by SC. So what is Z2? Z2 of S will be equal to parallel combination. So R2 into 1 by SC by R2 plus 1 by SC. That will be the net impedance Z2 of S. So on rearranging we'll get R2 equal R2 by Z2 of S equal to R2 by S into SC R2 plus 1. So this will be Z2. Okay, so this will be Z2 in S parameter. Okay, similarly, what is Z1? What is Z1 of S? Z1 of S equal to, since these two are in series, Z2 of S will be equal to R1, right? R1 plus 1 by SC. So on rearranging we'll get like SCR1 plus 1 by R1. So this is Z1. Okay, so what is so let me take another color. So what is T1 of S or T of S? T of S equal to Z2 by Z1. So what is Z2? Z2 is R2 by SC R2 plus 1. And what is Z1? Z1 is SC R1 plus 1 by R1. I think I'm correct. Okay. Okay. On rearranging, what we'll get? We'll get this R1 term will go above, right? Okay. So R1 into R2 by SC R2 plus 1 into SC R1 plus 1. I believe it's correct. Okay, I have done a mistake here, right? So this is not here in this term, it is like the denominator term is SC. I'm really sorry. So substituting here it will be SC. So it's not R1, it is R2 into SC. Okay, R2 into SC. Okay, so this is the term that we get here. Okay, so this is actually the transfer function. So let me write only that term, that is the end term, that is T of S equal to so SC, what was the term? SC into R2, right? So SC into R2 by SC R1 plus 1 into SC R2 plus 1. So from here it is clear, like if we analyze this transfer function, it is clear, like at S equal to 0, T of S is 0, right? And since the above term, it is like S into R2C. So what happens is like till and there and we'll see the when we see the poles at the denominator, that is a pole is like one pole is P1 equal to 1 by CR1 and the other pole is like P2 equal to 1 by CR2, right? So till that pole, either P1 or P2, this will be like it will be an incrementing value at 20 dB per decade, and at the particular pole we don't know whether it is P1 or P2, we just need to determine that. So say for example Pi, at that Pi it will be 0 dB, right? And in the next means like, since it is 20 dB per decade initially, at one pole, either P1 or P2, it will create a minus 20 dB and it will create 0 dB per decade, and that is a passband. And at the next, say for example Pj, we don't know other again P1 or P2. So at P1 or P2 again there will be minus 20 dB, so it will create such a response, minus 20 dB per decade. So this is actually a band pass filter. Okay, so we need to determine which one, like whether P1 or P2, who is the lower cutoff frequency. So Pi is actually FL, right? If it is frequency, it is FL, and Pj is the FH. So in angular frequency, it is omega L and omega H. So we need to determine which term, whether it's the R1C or the R2C, that creates the lower and higher cutoff frequency. So for that we need to analyze this circuit. So suppose I am giving a source, a sinusoidal source, okay, and its frequency is varied. Okay, so suppose if the frequency is 0, like f is equal to 0, what happens is like the impedance across the capacitor will be high, right? It will be like infinity, so it will be like open, minus plus, and there is one resistor here, it will be like open. Okay, so V1 at DC, 0 frequency. Okay, so this will be open. So what happens? There is no current, there is no input voltage, right? So if there is no input voltage, V0 will be equal to 0. That's what we have seen here. At frequency equal to 0, or and transfer function at frequency equal to 0, the T of S will be equal to 0. Okay, now when frequency is increased, okay, when frequency is increased, what happens? There is a drop. There is a impedance across the capacitor, that is 1 by SC, that is 1 by j omega C, or 1 by j 2 pi fc. So as the frequency increases from 0, this impedance across the capacitance, say ZC will start decrementing, right? So initially at lower frequency, this capacitance will impart very high impedance. So this capacitors will impart very high impedance. So it is almost like there is a very high impedance resistor kept in series with R1. So if it is a series combination, the entire voltage will actually drop across this resistor, right? If say if this is ZC, it's very high than R1. What will happen? The Vin will be almost dropping across this ZC. And what about here? Since this is like a resistor ZC kept in parallel with R2. So since ZC is very higher than R2, it is more or less like R2. Like there is no effect of ZC. Okay, so when the frequency increases, the ZC start decrementing. Okay, so at a particular point, ZC will be almost comparable with R1, and again for a very high value, ZC will be negligible compared to R1. Okay, so at that value, whatever the input given, it will be more or less like given as input to the point R1, or at this node of R1. So that is the first cutoff frequency. So let me clear all this. I will explain once more. So when so for example this is R2 and this R1, and I will write it as ZC and this ZC. Why I draw it like this? I am assuming like it's a impedance due to the capacitor, and I am just comparing ZC and R1. So for a value when ZC is very high, when the frequency is very low, ZC is very high, and whatever the input is given will be dropping across the ZC. So that is what happening. Okay, and similarly here ZC is very much higher than R2, which means it is like more or less like an open configuration. So it will be somewhat like this. Okay, so it will be somewhat like this. So this is R2, this is R1, and there is an impedance ZC. Okay, so here since in order to make it a bandpass filter, we will select the value of ZC, or the value of capacitance, and the value of R1 and R2 in such a way that initially the ZC will start increasing, right? From infinity it will start decrementing. It will decrement to a value such a way that at a particular frequency, say at a particular frequency FL, the ZC will be very much less than R1. So what happens if ZC is very much less than R1? At that point this will be short circuited, or this will be short circuited. Okay, and what about this? This is open already. R2 is very kept very high. So at that time it will work as a normal inverting configuration. Okay, so that is the first cutoff. So this will be the first cutoff, and that is due to the value R1 and C. Okay, so after that it will be working as an inverting configuration. Now again the frequency is incremented, and at a particular frequency the impedance of ZC will again reduce in such a way that the ZC will be again very much less than R2. At that particular point what will happen? This will start, like, the impedance due to this ZC will be more, means impedance will be due to ZC will be less. So what happens is the net impedance of this capacitor resistance will be more or less equal to ZC. Okay, so R2 will be lesser than ZC. So the net effect of this impedance will be due to ZC. So at that point what happens? The net output voltage will be somewhat, we can write that ZC by R1 or ZC parallel R2, while if ZC is much less than R2 means it will be like ZC by R1. Okay, so from that point it will start decrementing. So what is the higher cutoff frequency? Higher cutoff frequency is determined due to the resistance R2 and C. Okay, I think I made the point clear. So we were determining which all resistance is results in lower cutoff frequency and higher cutoff frequency. So which resistance and capacitor? This R1 and the capacitor C will result in lower cutoff frequency, and R2 and C will result in the higher cutoff frequency. Okay, so so in the transfer function that we derived, the derived transfer function was like this, right? So T of S equal to this term. Okay, so R1 into this 3 pico means the capacitor C. So 3 pico into R1. So 1 by R1 into 3 pico. This is the this will result in omega L, lower cutoff frequency, and this R2 1 by R2 into 3 pico will be equal to omega H, that is higher cutoff frequency. So we have already found what is FL. FL, it is given like 10 megahertz, and FH is given as 30 megahertz. Okay, we just need to substitute here. So we'll get like R1 equal to, on substituting we'll get R1 equal to 5.3 kilo and R2 as 1.768 kilo. So we have just substituted FL, FH in these equations, and we have found out what is the value of R1 and R2. So I think it's clear. So I will just again brief what I have done. So the question is to find what is the value of R1 and R2 such a way that the bandwidth of this bandpass filter is 20 megahertz, and the lower cutoff frequency is 10 megahertz. So FH we know from there it is 30 megahertz. So we need to find the R1 and R2. So for that we need to find what is the transfer function. So T of S equal to V naught of S by V1 of S. And what is V naught of S by V1 of S? It is like the impedance in the feedback, that is Z2, and at the input, impedance at the input Z1. So minus Z2 by Z1 is the V naught by means transfer function. So on substituting Z2 and Z1, we will get a transfer function like this in terms of S. And I just explained how we should consider the lower and means which all components will lead to lower and upper cutoff frequency. So based on that, we found that R1 and C results in the lower cutoff frequency, and R2 and C results in higher cutoff frequency. Then only it will act as a bandpass filter. So omega L will be equal to 1 by 3p into R, where 3p means capacitor, 3 picofarad capacitor, and omega H 1 by 3p into R2, where 3p is again the capacitor. We'll substitute FL and FH here that we have derived, and we'll get what is the value of R1 and R2, and R1 value is 5.305 kilo ohm and R2 is 1.768 kilo. So this is all about the questions that are that we have collected and solved. So I think it's clear to all. We can, so if you have any doubt you can ask. Hi, yes, hello. Last part means last question. Hello, last question. So you have understood how to find a transfer function and all, right? Transfer function you have understood, and you understood why R1C is taken as the reason for lower cutoff frequency and R2C for higher cutoff frequency. That okay. I will just make it clear once more. I'm sorry. So like so say I have connected one signal source here. Okay. So suppose, and let us write this as 1 by SC. Okay, 1 by SC, and this is 1 by SC. Okay, so suppose the input signal frequency is f equal to 0. So what happens is the circuit will be like open, right? The circuit will be open. It will be somewhat like this. Okay, so that's why at frequency f not equal to 0, it is 0. Okay, that's why at frequency f not equal to 0, the output is 0, because input is though there is some input, there is no, means like the entire input is dropped across this capacitor, so there is no input to the actually to this amplifier, so the output will be 0. Okay, so but according to the band pass filter transfer function, it must look like this, right? Which means after a particular frequency, see, after a particular frequency, it should not be like the output should not be affected by the frequency for a particular band, from this band to this band. That is, it must be somewhat like this. That is, there is no effect of capacitor. Okay, so this is R1, this is R2. Okay, so this must be almost like this. That is, this capacitor is being shorted. It must be so. Okay, it must be somewhat like this. Okay, so after the cutoff frequency FL, this filter must act like an inverting configuration. That is, there is no effect of what the capacitor see. This must be open and this must be short. Okay, so but initially it is like there is some capacitor, right? Here at input there is some capacitor. So when the frequency increases, what is the impedance due to this capacitor? That is 1 by SC or 1 by j omega c. So when the frequency increases, the impedance, say ZC, will start decrementing, right? When a frequency increases, the ZC will start decrementing. So at a particular point, this capacitor should act as a short, or in other words, we can say like the voltage drop across this capacitor must be negligible as compared to drop across R1. So when it happens, when ZC is very much less than R1. So this is the first case. Okay, this is the first case. That is, frequency at a particular frequency, ZC must be very much less than R1. At that case only, this capacitor will be short circuited, and this will be open compared to R2. So that frequency is FL. That frequency is FL. So which component results in FL? This capacitance C and this R1. Okay, so this is the relation between R1 and capacitance C will result in this lower cutoff frequency. Okay, similarly, when the frequency is again increased, okay, understood? Yeah, when frequency is increased, this capacitance impedance is decreased at a particular value. This will short circuited, or the impedance across ZC will be very much less than R2. So what is the which factor results in FH? That is R2 and C. Okay, I think it's clear. Okay. So let me check some questions. Okay. So any doubts, anyone? Hello? Hello? Hello. Yeah, sure. Yeah, you are audible, please. Please. Correct. Allow that input signal. Okay, I understood. Like, definitely. I will tell you. Yeah. So like, say for example, after FL. Okay, so after FL it is somewhat short here, and there is only resistance R1. Okay. So here there is one resistance R2, and there is a capacitor here C. So what happens is, like, after so till R2 is much greater than, say I mentioned this as ZC, so much greater than ZC, the net impedance will be approximately equal to R2. But at a particular frequency, R2 will be comparable with ZC. So what happens is, we cannot say like the entire Z2 is equal to R2. We will say Z2 equal to, what happens is Z2 equal to R2 by SR2 C plus 1. This is the impedance Z2. Okay. Now when we say it is like R2 by J omega R2 C plus 1. So in effect, like when this frequency increases, from that point, like when R2 and C is comparable, and we can consider this Z2 as this, when the frequency omega increases, Z2 will start decrementing, right? So what is the voltage V0 is Z2 minus Z2 by, now Z1 is R1, so Z2 by R1 into V1. So V1 is input. So when Z2 means omega start increasing after some cutoff frequency, say omega h, what happens is, like Z2 will start decrementing. As Z2 decrements, V0 also start decrementing. So that is what it is shown as this one. So how it decrements, since the denominator is like having only power n equal to 1, right? So it will decrement as minus 20 dB per decade. Is it okay? Is it fine? Okay. Sorry. So any other? So the session is till 9, so you can ask any question till that. I will be online till that time. Yeah, you are audible. Yeah, please. Hello? Means should I explain, or just I should show the questions only? Question only, right? Yeah, this is the first question. Okay, this is the first question. Determine the gain of circuit. Okay, it's non-ideal non-ideal op-amp is taken. So the question is to find the gain of the circuit. And the next question is the same question, but it is asked to determine the input resistance. So just need to rearrange and we will get the input resistance here. Third question is like band gain bandwidth product is given, and also the gain of that op-amp is given, or the configuration of the means inverting op-amp configuration is given. The question is to find the bandwidth, so we just need to substitute and we will get the bandwidth. So that is the third question. Now fourth question is find the output of this circuit, and again it is a non-ideal circuit, and it has offset voltage is given. You need to find the voltage V0. So it's again straightforward. We can substitute and we'll get output voltage V0. Fifth question is to determine the value of R2 such that the effect of bias current is nullified. So that is again we can find it. We just need to find the substitute the bias current in the circuit and we'll find that. Sixth question is like a transfer function is given, and we need to determine the corner frequency. Again it's a straightforward question. We can directly find from its transfer function. Seventh question is to find the transfer function in terms of S. So Bode plot is given, we need to find the transfer function. So we know the general form of transfer function in terms of S, and we found which all points are poles and 0. We just substituted and we got the transfer function. Eighth question is plot the Bode magnitude plot. So transfer function is given, we need to plot the Bode magnitude plot. Ninth question is to determine the value of n such that phase plot of the transfer function is given. So we initially find the angle of the transfer function and substitute omega equal to 0 and we will get n equal to 1. And 10th question is what we discussed just before, like the circuit is given, band pass filter is given, the bandwidth of the band pass filter is also given, lower cutoff frequency is given. We just need to find what is R1 and R2. We need for that we will find the transfer function and substitute the values, and we will determine initially which factors or which components should result in lower and higher cutoff frequency, and we will substitute. That's it. 10 questions. Okay. Sir, when will there be a problem solving session for week 3? So my session is next Tuesday. I think you can check the mail, like there are two or three sessions, online session being taken. Like you check the mail, previous mail, so each are on various day. For my session is on Tuesday, every Tuesday. I think this the upcoming week there are 2 sessions for third week session, so you can sit for that. Also NPTEL has shared the link, means we have uploaded the videos, so you can even check that. Sure, sure. Like I'm also not clear about like what regarding date and all. It is being mentioned by NPTEL. Mostly like what all being covered here. Like I think it's in most of the part will be those question will be which is covered in assignments. I think that is far enough for you people to solve the questions in examination. That actually I don't know correctly in which format it mostly in the whatever format it's being given in the assignment, mostly that will be followed, I guess. If you want, I will just check and tell you in the next video. Okay. Hello. Okay. Yeah, sure. See whether it is electrical or electronics, for both to understand or to understand the concept, the first thing that we need to learn is, like, I'll just point it out, or okay, wait a minute. First thing is like we need to know KCL and KVL. That is the first thing, basic thing. So if you know KCL and KVL means, I think almost all the concepts being taught in electronics as well as electrical, means basic analog circuits based all portions we can understand. Almost 80% we can understand. So this is the basic thing. And second thing is like for understanding this is also required, like the transforms, that is also, I think like Laplace transforms and all we may require to know. So that also I think you people would have covered. So if you know all these basics, it is very easy to understand the analog circuits. The just thing is like based on this concept you read. So I think the Rasavi, that book is very good also for analog circuits. The best book, the basic for to understand the basic knowledge, I think it's better to refer the microelectronics by Sedra and Smith. You would have Sedra and Smith heard here, right? So I think it's it will be easy for us to understand the concept. So basically, I think in the in that entire book they have discussed about BJT, MOSFET, FET circuits, and later later the op-amp based circuit also being given. Other Rasavi also, it's very good to start with that. So I think that's fine, right? Correct. Okay. Oh. Okay. Good. Okay. Okay, thank you. Sure. Always welcome. Sir, to what level or depth we need to learn mathematics? I think it's like it's basic, right? Like what all mathematics that we are doing, like as I mentioned earlier, we need to know KCL and KVL. If we know KCL and KVL, I think almost all mini circuits we can analyze easily. Just we need to know the concept, how to analyze it. Like for example, for an op amp, what is its characteristics? If we know its input impedance is very high and ideal characteristics, everything we know, means we can directly use that knowledge and these properties of KCL and KVL. We can directly find or we can easily solve the questions of analog circuits. What level means, you need to, like for example, if we need to check the frequency response, definitely we have to analyze, right, the frequency response of a circuit. Okay, so transfer function controlling part, like how whether it goes above means out of stability and all, we have to analyze that. For those part we have to we may need to know some of the Laplace transforms and all. So that will definitely help. Also, if we know some basics of differential equation, that will also help you. Differentiation, basics of differentiation and differential equation, that will also help us to model some of the components. Like if you go through the analog circuit book, we could see the how the BJT, even the op amp and all, how it is modeled, like equal model. So how it is being modeled, it is based on the current equation, and how the current equation is being simplified, and based on that how we can make the circuit. So for that we may require the basic knowledge of differentiation, even differential equations and all. So but we don't need much high level. Maybe for high level analysis we may require, but this is enough, I guess, from my basic knowledge. So I will show you. I think the NPTEL would have shared these links with you. So in this link, I will share this link. In this link, you can find the PPT that I used to prepare for every week for this TA ship. So you can go to it also. So I'll show you. So here week 1 and week 2 is there. Similarly, you can find the link for the week 1 class, like week 1 live class here in this. So it actually it is being mailed by NPTEL to you. So you can check that. Okay. So I think okay, that's fine. Okay, so okay then, let me wind this up. It's already 9. See you all in the next class. Thank you.